A mysterious roar from deep space defies all known laws of physics. Scientists call it the space roar, a deafening blast of cosmic radio waves 6 times louder than anything they thought possible. This is not a story from science fiction, but a real and unsolved enigma that directly challenges our fundamental understanding of the universe. By the end of this, you will understand the incredible detective story behind this signal and the mind-bending theories that try to explain why it exists at all. We will investigate where this overpowering noise could possibly be coming from and why even the most brilliant minds are struggling to find an answer. What does it mean to discover something the universe should not be able to create? This pervasive static was first picked up in 2006 by a NASA project named Arcade. The mission's goal was simple: to measure the faint heat from the earliest stars. Instead, its instruments registered something bewildering, a deafening hiss that washed over the entire sky. Think of tuning an old analog radio to a dead channel where the static is not just empty noise. That faint crackle is the cosmic microwave background, the remnant echo of the Big Bang. Now imagine turning the volume dial and hearing that static roar 6 times louder than it ever should. That is the scale of the anomaly scientists faced. This was not a signal from a single star or a distant galaxy. It was a uniform wall of sound coming from everywhere at once, a true background to the cosmos. All the radio waves from every known galaxy, every quasar, every star we have ever catalogued, when added together, still only account for a fraction of this immense noise. The universe, according to our best models, should be relatively quiet at these specific radio frequencies. The existence of this roar means there is a colossal source of energy out there, a fundamental piece of the cosmic puzzle that we have not yet identified, and it is broadcasting at a volume that defies all expectation. The Arcade mission was a masterpiece of engineering, a sophisticated instrument carried high into the stratosphere by a massive scientific balloon. Its full name, the Absolute Radiometer for Cosmology, Astrophysics, and Diffuse Emission, revealed its ambitious goal to listen for the faintest whispers from the dawn of time. Scientists hope to detect subtle variations in the cosmic microwave background, the afterglow of the Big Bang itself. To do this, Arcade needed to escape the noisy radio interference of Earth. It launched from a remote field in Palestine, Texas, and floated up to where the sky turns black, a silent sentinel above 99% of the atmosphere. There, in the profound cold and quiet, its supercooled instruments scanned the heavens, but what they heard was not a whisper, it was a scream. At a frequency of 3 GHz, a specific band where the universe was predicted to be serene, the sensors were flooded with an intense, unexplained radio hiss. The lead scientist, Alan Coggart, and his team were initially baffled. They meticulously checked and rechecked every possible source of error. Was it interference from the Earth below? No. Could it be emissions from the balloon itself or the instrument? They ruled it out. The signal was real, and it was coming from deep space. This was not the quiet cosmic murmur they had hoped to find. It was a deafening roar that their models of the universe had no room for, a fundamental discovery that was as thrilling as it was confounding. The universe, it seemed, was hiding a source of energy on a scale we had never before conceived. The predicted quiet of the universe makes this roar so deeply unsettling. Think of the cosmos as a vast, dark ocean. Scientists have mapped every known source of radio waves, every distant galaxy and brilliant quasar, like charting the individual ships on that ocean. They know how much noise each one should make, and when they add it all up, they arrive at a baseline, a gentle, expected hum for the entire universe. This is the cosmic radio background, the cumulative whisper of every star and galaxy we have ever seen or predicted. The space roar shatters that prediction. It is not just a little louder, it is 6 times more intense than that entire calculated sum. Imagine sitting in a silent, isolated room, expecting to hear only the faint, predictable ticking of a clock. Instead, you are met with the overwhelming, constant roar of a jet engine. The source of that noise is not just unknown, it is something our current understanding of physics says should not be there at all. Every conventional source has been counted, and still, this colossal, unexplained signal remains, a fundamental anomaly that points to a gap in our cosmic ledger, a source of energy so immense and pervasive that it rewrites the rules of what we thought was possible. So where could such an overwhelming sound possibly originate? One compelling line of inquiry points to the very dawn of creation itself. Scientists have proposed that the roar might be the collective voice of the universe's first stars and galaxies. Picture the cosmos in its infancy, a few 100 million years after the Big Bang. This was an era of dramatic formation, when the first monstrously large and active galaxies were igniting across the void. These primordial giants would have been incredibly energetic, blazing with the furious light of newborn stars and the violent processes around supermassive black holes. Such intense activity generates powerful radio emissions, and if there were trillions of these early galaxies, their faint, individual signals could have traveled across billions of years. Their collective radio whispers, stretched and softened by the expansion of the universe, might blend together into the diffuse, all-sky hiss we detect today. It is a beautiful idea that we are hearing the faint, fossilized echo of the first cosmic dawn. Yet, this elegant theory faces a formidable obstacle: the sheer volume of the roar. Our most powerful telescopes, like the James Webb Space Telescope, are peering back into this very epoch. While they are finding early galaxies, they have not found nearly enough of them to account for a signal this loud. The numbers simply do not add up. To produce the observed intensity, the early universe would have needed to be absolutely packed with radio-bright galaxies, far more than our current observations support. This leaves us with a haunting question: are our telescopes still missing a hidden population of these earliest objects, or are we listening to something else entirely, a phenomenon even more exotic and unexplained? Another cosmic structure holds a possible clue within its immense gravitational embrace. We must look to the great clusters of galaxies, the largest known organized assemblies of matter in the universe. Each cluster is a sprawling metropolis of thousands of individual galaxies, all bound together in a single, titanic system by the unyielding force of gravity. But the space between these brilliant islands of stars is not truly empty. It is filled with a searingly hot, incredibly thin gas known as the intracluster medium. Within this superheated plasma, electrons can be accelerated to nearly the speed of light. When these frenzied particles spiral along the weak magnetic fields that also permeate the void, they emit a specific type of radiation called synchrotron radiation, which we detect as radio waves. The theory suggests that if this faint, diffuse radio glow from the spaces between galaxies is far more common and far more powerful across the cosmos than our models predict, then the combined whisper from countless clusters could, in principle, build up into the pervasive roar we observe. It is a compelling idea that the answer lies not in the galaxies themselves, but in the vast, energetic seas that separate them. However, this hypothesis, too, struggles under the weight of the evidence. Astronomers have meticulously studied many of these colossal clusters, mapping their radio emissions in fine detail. While they do detect this intracluster radio haze, the signal is simply not strong enough. Even when we add up the potential contribution from every galaxy cluster we can see, the total falls dramatically short of accounting for that sixfold excess. The universe's background radio station is still playing at a volume that these cosmic cities cannot produce, leaving us to wonder what other, more hidden orchestra is performing in the dark. Perhaps the answer to this cosmic noise lies not in the stars or the hot gas between them, but in the universe's most elusive and abundant ingredient, dark matter. This invisible substance, which makes up roughly 27% of the cosmos, has so far revealed itself only through its gravitational pull on galaxies. We cannot see it or touch it, yet its presence is fundamental to the very structure of the universe. Some theoretical physicists have proposed a radical solution to the space roar, suggesting that certain types of dark matter particles could be responsible. The leading candidates are known as WIMP, or weakly interacting massive particles. The theory suggests that when these particles collide, they could annihilate each other in a flash of energy. Alternatively, some dark matter might simply be unstable, slowly decaying over eons. In either scenario, these processes would release energy, and some of that energy could manifest as the very radio waves we detect as the roar. It is an incredibly elegant idea, a two-for-one solution that would explain the nature of dark matter while simultaneously accounting for the mysterious radio background. Imagine if the faint hiss filling the cosmos was actually the sound of the universe's hidden skeleton slowly fizzling away. The appeal of this theory is undeniable, but it stands on shaky ground. Despite decades of searching with incredibly sensitive detectors, no one has ever directly observed a dark matter particle or confirmed that it annihilates or decays in this way. There is no experimental evidence to link this invisible substance to radio emissions. For now, this remains a fascinating and alluring possibility, a ghost of an explanation for a ghostly signal, reminding us that the most satisfying answers are not always the correct ones. When our standard cosmic inventory fails, we are forced to peer into the stranger corners of theoretical physics. Here, explanations for the space roar become as exotic as the phenomenon itself. Scientists have proposed sources that sound like pure science fiction, beginning with cosmic strings. Picture the fabric of space-time not as perfectly smooth, but as having tiny, fundamental cracks. Cosmic strings are hypothetical one-dimensional defects, theoretical wrinkles left over from the universe's violent first moments. As these unimaginably thin and dense filaments vibrate and snap throughout the cosmos, they could, in theory, release colossal bursts of energy, some of which might manifest as the very radio waves we detect. It is a breathtaking concept that the roar could be the sound of space-time itself cracking under cosmic strain. Yet these strings remain entirely hypothetical. No experiment or observation has ever confirmed their existence, making them a powerful idea without a shred of physical proof. Another possibility points not to one single exotic source, but to a hidden multitude. Perhaps the sky is filled with countless previously unknown types of radio transients, objects that flare with incredible brightness for only a short time. Or maybe a vast population of hyperactive neutron stars, the spinning, magnetized corpses of dead suns, are constantly emitting powerful radio bursts. The problem, as always, comes down to the sheer scale required. For any of these objects to account for the roar, they would need to exist in numbers so vast it defies belief, each one possessing energy outputs that push far beyond the limits of known stellar behavior. The universe would have to be teeming with these radio screamers, a cosmic cacophony so dense it challenges our most fundamental senses of the heavens. This forces a difficult choice. Do we accept that the cosmos is filled with bizarre, energetic objects we have simply never seen? Or is the truth something even stranger, something we have not yet even begun to imagine? This left the scientists with a chilling and undeniable conclusion. The roar was not a ghost in their machine. Before any grand theories about cosmic strings or dark matter could be taken seriously, the arcade team had to perform the most critical and tedious work of all. They had to prove beyond any reasonable doubt that they were not simply listening to their own equipment. Every scientific instrument, no matter how advanced, generates its own faint electronic whisper. The team embarked on a painstaking process of elimination, running their supercooled sensors in a vacuum chamber on the ground to map every last bit of noise the device itself could produce. They calculated the precise radio signature of the Earth's atmosphere below them. They modeled the emissions from the massive scientific balloon that carried their payload, ensuring its fabric and structure were not the source. Every potential contaminant was hunted down and quantified. The signal remained clear and overpowering. The final, crucial validation came from other ears listening to the sky. Independent analyses of data from other radio telescopes, instruments built with entirely different designs and located in different environments, began to pick up the same anomalous background static. This cross-confirmation was the final nail in the coffin for the instrumental error theory. The space roar was not a glitch. It was a feature of the universe, a real and pervasive sound from the depths of space that our current map of reality cannot explain. The hunt for the source of this cosmic noise demanded a second opinion. In the years following the Arcade balloon flight, an entire generation of new radio telescopes turned their collective ears to the sky. On the ground, instruments like the giant meterwave radio telescope in India and the sprawling Murchison Widefield array in the remote Australian outback began their own deep listening campaigns. Their mission was twofold: to confirm the roar was not a solitary anomaly and to dissect it with an even finer surgical precision. These observatories are technological marvels, capable of tuning into different frequencies with a sensitivity far beyond what was possible before. They scanned vast stretches of the heavens, not for a single bright object, but for the faint, diffuse glow that makes up the background itself. This is the scientific process at its most vital, independent verification. By observing the same phenomenon with different tools from different locations and at different wavelengths, researchers could be absolutely certain the signal was a real property of the cosmos and not an artifact of one particular instrument's design. Each new data set was a crucial piece of the puzzle, helping to refine the exact profile of the roar, mapping its subtle variations across the sky with ever greater detail. The goal was to find a crack in the uniformity, a slight brightening in one specific direction that might point toward its ultimate source. If the roar was indeed the combined whisper of the first galaxies, then these powerful new telescopes should have been able to pick out the faintest, most distant members of that hidden population. They should have seen the individual trees that make up the forest, yet as the data poured in, the results were both confirming and deeply puzzling. The roar was undeniably there, a consistent feature across multiple independent surveys, but the anticipated legions of faint radio galaxies simply did not materialize in the numbers required to explain it. The universe, it seems, was still hiding its greatest radio station, forcing astronomers to listen even more carefully, to ask even more fundamental questions about what or who is broadcasting. This process of isolating the true cosmic signal is like trying to hear a single, faint whisper in a crowded, roaring stadium. All around us, the cosmos is blaring with radio noise that has nothing to do with the mysterious background roar. Our own Milky Way galaxy is a brilliant, swirling disk of radio light, a foreground fog that must be meticulously mapped and digitally peeled away. Then there is the constant crackle of human civilization, the radio and television broadcasts, the satellite transmissions, and the radar pulses that leak upward into the sky, creating a shimmering veil of interference. To see past all this, astronomers become cosmic accountants, using incredibly sophisticated statistical models. They observe the sky across many different radio frequencies, building a precise profile of how the Milky Way glows and how human noise pollutes the view. They then run their algorithms to subtract these known foregrounds, like carefully cleaning a dirty window pane, hoping to reveal the clear, distant view of the cosmic background static behind it all. The sheer complexity of this task means the results are always under intense scrutiny. A tiny miscalculation in modeling the galaxy's own emissions, or an unaccounted-for source of human interference, could theoretically leave behind a false residue, an artificial signal that looks like the roar but is just the ghost of a subtraction error. This is why the scientific debate continues, not about whether the signal exists, but about its true, unadulterated intensity. Every new observation and every refined model is a test, a challenge to see if this cosmic roar grows louder, grows softer, or simply vanishes back into the noise from which it came. The profound difference between this unexplained roar and the universe's other great background signal reveals just how strange it truly is. We have already mapped the cosmic microwave background with exquisite precision. That signal is the remnant heat from the Big Bang itself, a thermal echo that has cooled to just a few degrees above absolute zero as the universe expanded. It is a smooth, predictable bath of microwave radiation that perfectly matches our theories of the universe's explosive birth. The space roar is its complete opposite. This is a non-thermal radio background, a hiss that does not come from the gentle warmth of a cooling fire, but from the frenetic, high-energy motion of particles. One was a triumphant confirmation of our cosmic origin story. The other is a glaring question mark, an anomaly that arrived without an invitation. This stark contrast highlights a critical gap in our knowledge. The cosmic microwave background represents the universe's first baby picture, a relic we understand deeply. The space roar is a voice from its awkward teenage years, a phase of intense, energetic activity that our current family album of the cosmos seems to be missing entirely. Its very existence tells us that our census of the cosmos is woefully incomplete. There are either colossal energetic processes we have not yet accounted for, or entire populations of incredibly radio-loud objects that have somehow remained invisible to our most powerful telescopes. This is not a minor accounting error. It is a fundamental piece of the cosmic ledger that has gone entirely unrecorded, suggesting the universe is far louder and far more mysterious than we ever dared to believe. This roar from the cosmic dawn would fundamentally rewrite the first chapters of our universe's story. We call this ancient period the epoch of reionization, a time when the cosmos transformed from a dark, featureless sea of primordial gas into a brilliant landscape of light. The very first stars and galaxies were flickering on, and their intense ultraviolet radiation began to tear apart the atoms of hydrogen that filled all of space, a process known as reionization. It was the universe's great awakening, but we know very little about this crucial era. How many of these first galaxies were there? How big and bright were they? How quickly did they ignite and begin to reshape their surroundings? The space roar could be the direct evidence we have been missing. The intensity of this radio background is not just a volume knob. It is a fossil record. The sheer power of the signal could tell us about the formation rates of those first structures. A louder roar would imply a universe that was packed with stellar nurseries, where galaxies formed in a frantic, explosive rush. A quieter signal would suggest a slower, more gradual dawn. Furthermore, the specific frequency of the emission holds clues about the masses and properties of the stars themselves. Were they predominantly colossal, short-lived blue giants, burning furiously and dying young? Or was there a more diverse population? The radio waves we detect are a direct product of the violent processes within those first galaxies, from supernova explosions to the frenetic activity around nascent black holes. By decoding this persistent hiss, we are not just identifying a source of noise. We are listening to the birth cries of the very first structures in the cosmos, a live broadcast from the universe's infancy that has taken billions of years to reach our instruments. This makes the roar far more than a mystery. It is a potential key, a direct line back to the moment our cosmic house was built, waiting to tell us who the first architects were and how they did their work. This search for the roar's origin is a cosmic fishing expedition, but scientists are not hunting for one giant whale. They are trying to net a galaxy of minnows. The core strategy is to find countless discrete sources, individual points of radio light so faint and distant that their combined whisper would build into the deafening roar. If the roar is the sound of a cosmic crowd, then astronomers need to identify every single person in that crowd. This requires looking deeper into space than ever before, pushing our telescopes to their absolute limits. Instruments like the Jansky Very Large Array, a sprawling network of radio dishes in the New Mexico desert, act as immense ears. They focus on tiny, seemingly empty patches of sky for hundreds of hours, collecting every stray photon of radio energy. In these deep field observations, what appears as a blank void to a less powerful instrument slowly blossoms into a universe teeming with faint radio galaxies. Each one is a potential contributor to the background static. The ultimate hope for this search rests with the Future Square Kilometre Array, a revolutionary observatory being built across South Africa and Australia. Its name is literal. It will have a total collecting area of 1 square kilometre, making it the most sensitive radio telescope ever conceived. It is designed to see these faint radio whispers directly, to conduct a cosmic census of such profound depth that it could finally count all the missing galaxies. Finding them would be a monumental discovery, solving the mystery by showing that the universe is simply more populated with radio-bright objects than we ever knew. But if even this incredible machine stares into the void and finds it still not loud enough, then the mystery of the space roar will only deepen, forcing us to accept that the explanation is something far stranger than a universe full of hidden stars. When every star, every galaxy, and every known particle has been counted and found wanting, we are pushed to the very edge of physics itself. The relentless, unexplained volume of the space roar forces a humbling admission. Perhaps our current rulebook for the universe is incomplete. This signal could be the first direct evidence of a process we have not yet named, a fundamental law of nature operating on a cosmic scale that our theories have failed to predict. It might be the signature of novel particle interactions, where exotic forms of matter collide and release energy in ways we cannot yet replicate in our largest particle colliders. Or it could point to the unexpected behavior of magnetic fields, those invisible forces that weave through the cosmos, perhaps capable of amplifying radio emissions in ways we never thought possible across billions of light years. Some theorists even dare to connect it to the most profound mystery of our age, dark energy. This is the unknown force driving the accelerated expansion of the universe. Could the roar be a secondary effect of this expansion, a faint sonic boom from the stretching fabric of space-time itself? These are not ideas scientists propose lightly. Invoking new physics is a last resort, a step taken only when every conventional box has been checked and every familiar explanation has crumbled. Yet history tells us this is precisely how science evolves. The orbit of Mercury deviated slightly from Newton's predictions, a tiny anomaly that was only resolved by Einstein's theory of general relativity, completely rewriting our understanding of gravity. The faint, fixed pattern of the cosmic microwave background was itself a shocking discovery that cemented the Big Bang theory. Anomalies are not just problems to be solved. They are doors waiting to be opened. The space roar, in its deafening persistence, is not merely a puzzle. It is a potential invitation to glimpse a deeper layer of cosmic reality, a clue that the universe still holds its greatest secrets close. The space roar resonates so deeply because it is a perfect cosmic riddle. It is not a fleeting signal from a single point, but a constant, overwhelming presence that defies simple explanation. For the public, this is not just another scientific headline. It embodies the profound and humbling truth that the universe is still fundamentally wild and unknown. We have sent probes to the edge of our solar system and built telescopes that see back to the dawn of time, yet the sky itself whispers with a secret we cannot yet decipher. This persistent hiss is a powerful reminder that for all our knowledge, we are still children listening at a door, trying to understand the conversation happening on the other side. It taps into a primal sense of wonder, the same feeling that made our ancestors look up at the stars and dream. In an age where so much seems mapped and explained, the raw is a gift of enduring mystery. Within the scientific community, this mystery is a powerful engine for progress. The raw is a concrete problem that refuses to go away, a constant thorn in the side of our standard models of the cosmos. It is a frequent and heated topic at major international astronomy conferences, where theorists and observers gather to debate the latest data and propose ever more inventive solutions. Peer-reviewed papers are published regularly, each one a new attempt to build a mathematical framework that can contain this deafening noise. Does it come from a hidden population of galaxies? Is it the signature of decaying dark matter? Could it be evidence of cosmic strings? Each hypothesis is rigorously tested, and each so far has fallen short. This collective effort, this global conversation spanning decades, demonstrates the relentless and collaborative nature of science at its best. It is not a solitary genius who will crack this case, but a worldwide community of curious minds, all driven by the same fundamental question. The raw is more than a signal, it is a catalyst pushing our technology, our theories, and our very understanding of reality forward, one frustrated and fascinated scientist at a time. This immense challenge of sifting through cosmic data is not one that professional scientists face alone. The sheer volume of information gathered by modern radio telescopes is staggering, creating a digital universe so vast that no single research team could ever hope to analyze it all. This is where the power of the global community comes into play, transforming a specialized scientific quest into a collective human effort. Platforms like Zooniverse have opened virtual doors, inviting anyone with curiosity and an internet connection to become a cosmic detective. Imagine logging on and being presented with real, unprocessed images from a major radio sky survey. Your task is to scan these intricate maps of static, looking for faint smudges or unusual patterns that a computer algorithm might have incorrectly dismissed as noise. The human brain possesses an extraordinary, almost intuitive ability for pattern recognition, a skill that even our most advanced artificial intelligence can struggle to match. A volunteer might spot a faint, diffuse cloud of radio emission that represents a distant galaxy cluster, or a strange, twisted shape that could be the signature of two galaxies colliding. Every click, every classification made by a citizen scientist contributes a small but vital piece to the larger puzzle. This process of distributed discovery does more than just accelerate research. It fundamentally changes who gets to participate in science. By engaging the public directly, the search for the source of the space raw becomes a shared adventure. A teacher in Brazil, a student in Japan, and a retiree in Sweden can all look at the same slice of the sky, united by the common goal of unraveling a cosmic secret. This inclusive approach builds a worldwide community that is personally invested in the outcome, fostering a deeper public appreciation for the scientific process itself. It transforms the abstract concept of the raw into a tangible mystery that thousands of hands are helping to solve, proving that the greatest enigmas of the universe are not just for experts in lab coats, but for all of us to explore together. Cracking this cosmic case will demand tools that do not yet exist. Our current telescopes, as powerful as they are, remain deaf to the faintest whispers that might compose this overwhelming roar. The next leap forward rests with the Square Kilometre Array, a project of such staggering ambition it redefines the scale of scientific exploration. This is not a single telescope but a vast network of thousands of antennae spread across 2 continents in the remote deserts of South Africa and Western Australia. Its name is a literal promise, a combined collecting area of 1 square kilometre that will make it the most sensitive radio ear ever pointed at the sky. With this immense power, the SK will conduct a cosmic census of unparalleled depth. It will peer back to the very first stars and galaxies, not as a fuzzy, indistinct background, but as a field of individual points of light. The great hope is that it will finally see the hidden population of faint radio galaxies, counting them one by one to see if their combined murmur truly adds up to the deafening roar we hear. If it finds them, the mystery is solved, but if it stares into that ancient void and the numbers still fall short, the enigma will transform into something even more profound. Yet the sheer volume of data the SKA will generate presents a challenge of its own. Every day, it will produce more information than the entire global internet traffic. Sifting through this digital universe to find the subtle patterns that explain the roar will require a revolution in computing. This is where artificial intelligence enters the story, not as a replacement for human curiosity, but as an essential partner. Advanced machine learning algorithms will be trained to scan these colossal datasets, identifying the faint signatures of distant galaxies or the diffuse glow of intergalactic gas with a speed and accuracy no human team could ever match. Furthermore, the answer may not come from radio waves alone. The future lies in multi-messenger astronomy, a coordinated effort to observe the cosmos across every wavelength and particle. By combining the SKA's radio findings with infrared views from the James Webb Space Telescope, X-ray data, and even detections of gravitational waves, we can build a multidimensional picture of the cosmos. A slight brightening in a radio map when paired with a specific gravitational wave signal could reveal a previously invisible cataclysm. This collaborative approach turns every observatory into a single instrument, all tuned to listen for the same answer. The path to understanding the space roar is not a straight line. It is a journey that will be paved with silicon and steel, guided by algorithms and human ingenuity, all in pursuit of a sound that has traveled across the ages to ask us a single, simple question. Whenever we hear about a mysterious signal from the cosmos, our minds leap to the most thrilling possibility. Could this finally be it, the long-awaited sign that we are not alone in the universe? This instinct is powerful, but in the case of the space roar, it leads us down the wrong path. The scientific community has overwhelmingly ruled out an intelligent extraterrestrial source for one simple reason: the nature of the signal itself. A message from another civilization, whether a deliberate beacon or the leaked chatter of an advanced society, would almost certainly possess a certain fingerprint. It would be structured, it might be concentrated, coming from a specific point in the sky. It could be pulsed or modulated, carrying information in its patterns. The space roar exhibits none of these traits. It is a formless, uniform hiss, the same in every direction, with no discernible pattern, no repetition, and no variation. It is the cosmic equivalent of listening to the steady, featureless sound of rain on a roof, not the complex symphony of a radio broadcast. This is not the signature of technology. It is the signature of a vast natural process, a fundamental engine of the cosmos that operates on a scale we are only beginning to grasp. While the idea of an alien civilization sending a signal so powerful it drowns out the entire universe is a fantastic story, it simply does not align with the evidence we have in hand. The roar is not a message, it is a physical phenomenon, a cosmic weather pattern of immense proportions, and its explanation, while still hidden, lies within the realm of astrophysics, not biology. The truth is, a natural explanation is often far more profound than a speculative one. Unraveling the source of this roar won't just tell us if someone is out there. It will reveal a fundamental and perhaps entirely new chapter in the story of how our universe works. Solving a cosmic mystery like the space roar will not put a more powerful computer in your pocket tomorrow. The value of this pursuit is far more profound and far-reaching. It lives in the invisible engine of progress, where the quest to answer a fundamental question forces us to build better tools, and those tools, in turn, reshape our world. Consider the technology behind modern WIFI. Its foundations were laid by radio astronomers studying distant quasars, work that required decoding faint cosmic signals and minimizing interference. The same goes for the sensitive detectors used in medical MRI machines. which share a technological heritage with the instruments that listen to the universe's whispers. Every time we push the boundaries of a field as demanding as radio astronomy, we are forced to invent. We create more sensitive receivers, more powerful data processing algorithms, and more sophisticated materials. These innovations do not stay locked in an observatory. They trickle out, finding new life in hospitals, in communication networks, and in our daily lives, becoming the unheralded dividends of pure curiosity. This technological spin-off is a silent partner to discovery, a tangible return on an investment in wonder. Beyond the circuitry and software, the cultural impact of a mystery this grand is immeasurable. The space roar is not just data on a scientist's screen. It is a story. It becomes the subject of documentaries that captivate millions, the central theme of novels that explore the edges of human knowledge, and the inspiration for artworks that try to capture the feeling of a universe that speaks in a language we have yet to understand. This mystery captures the imagination of a child gazing at the stars, planting a seed that might one day grow into a career in science or engineering. It reminds all of us, regardless of our profession, that we are part of a species driven to look up and ask why. This shared sense of awe, this collective yearning to solve a puzzle that spans the entire cosmos, is a powerful cultural force. It enriches our global conversation, fuels our creativity, and ultimately propels our entire civilization forward on a wave of innovation born from a simple, beautiful need to know. This puzzle is too large for any one field of science to solve alone. Unlocking the secret of the space roar demands a symphony of experts, each bringing a unique instrument to the cosmic orchestra. Radio astronomers provide the initial data, the raw recording of the sky's strange hiss. But to interpret it, we need cosmologists who can run supercomputer simulations of the early universe, testing whether their virtual realms of primordial galaxies can produce a roar this loud. When those models fall short, the baton passes to particle physicists. They are the architects of the invisible, proposing new types of dark matter and calculating whether their theoretical collisions could generate the precise radio signature we observe. Meanwhile, plasma physicists scrutinize the behavior of superheated gas in galaxy clusters, searching for some overlooked mechanism that could amplify their faint radio whisper into a shout. And underpinning it all are the computer scientists who design the brilliant algorithms that can sift through a universe of digital noise, separating the true cosmic signal from the endless foreground interference. This is not a linear process, it is a dynamic, collaborative dance. A cosmologist's new model might suggest a specific target for a radio telescope. A particle physicist's novel idea about dark matter decay could send everyone back to reanalyze old data with a fresh perspective. This fusion of disciplines is the new frontier of discovery. The greatest mysteries of the cosmos no longer fit neatly into the old boxes of astronomy or physics. They exist in the fertile spaces in between, where different ways of thinking collide and spark new ideas. The space roar is more than a signal, it is a bridge connecting experts who once spoke different scientific languages into a unified team, all focused on deciphering the same profound message from the dark. The space roar stands as one of modern cosmology's most profound and stubborn puzzles. The next decade, however, promises to be a turning point, armed with a new generation of instruments being built right now. The full deployment of the square-kilometer array will be like turning on the universe's finest hearing aid, allowing us to listen to the cosmic dawn with a clarity we have never before possessed. Alongside it, new space telescopes will join the hunt, scanning the heavens in complementary wavelengths of light. We are on the verge of gathering the most detailed census of the early universe ever attempted. This flood of new data will force a resolution. Either we will finally pinpoint the countless faint radio sources that create this collective sound, or we will be left with an even more startling realization. If we look with this incredible power and still cannot find enough galaxies to account for the roar, then the mystery deepens into something far more radical. We would have to conclude that the source is not just hidden, but fundamentally different from anything in our current cosmic inventory. This journey of investigation, with all its false leads and thrilling possibilities, is as crucial as the final answer itself. The enduring presence of this anomaly guarantees that cosmology remains a living, breathing science, perpetually on the verge of a revolution. It is a constant reminder that the universe is not yet done surprising us, and that our greatest discoveries often begin with a sound we do not understand. This relentless, unexplained static is far more than a scientific curiosity. It represents a fundamental gap in our cosmic ledger, a glaring error in our accounting of the universe's total energy budget. We think we know what makes up the cosmos, from the stars we see to the dark matter we cannot. We have models that predict how galaxies form and evolve over billions of years. Yet the space roar tells us, in no uncertain terms, that a colossal source of energy is missing from our calculations. It is as if we carefully added up every known expense in a vast corporation, only to discover that our books are still billions of dollars in the red, with no record of where that immense expenditure went. Finding the source of this roar is not just about solving a puzzle. It is about correcting our most basic blueprint of reality. If the roar comes from those first galaxies, it would force a complete rewrite of the universe's early chapters, revealing a period of frantic, explosive star formation far beyond our wildest estimates. This would reshape our entire understanding of how cosmic structures are born. If it is tied to dark matter, we would have our first tangible clue to the nature of this invisible substance that binds the cosmos together, moving it from a theoretical ghost into the realm of observable physics. And if it is something else entirely, a new phenomenon or a previously unknown particle interaction, then we are on the verge of a discovery that could open a whole new field of astrophysics. This is the true value of the mystery. It is a catalyst. The relentless, humbling presence of this signal pushes scientists to build better telescopes, to devise more creative theories, and to collaborate across disciplines they never thought to connect. It forces us to admit that for all we have learned, the universe is still capable of profound surprises that challenge our core assumptions. This pursuit, this drive to answer a question that nature has so boldly posed, is the very engine of science. It is what compels us to look deeper into the darkness, not because we know what we will find, but because we cannot bear the thought of leaving the question unanswered. The space roar stands as a lasting testament to a cosmos still rich with secrets. It reminds us that for every question we answer, the universe poses another, more profound one. This journey began with a single, baffling balloon experiment and has since spiraled into a global scientific endeavor, pulling in the minds of astronomers, particle physicists, and curious citizens alike. We have walked through the possibilities, from the collective birth cries of the first galaxies to the ghostly decay of dark matter and the theoretical cracks in space-time itself. Each theory is a potential key, yet the lock remains stubbornly shut. The definitive truth is still a whisper on the cosmic wind, just beyond the reach of our most powerful instruments. This is the true thrill of exploration, the understanding that the greatest discoveries are not in points but new beginnings. So we leave you with this question. Where does your intuition lead you in this cosmic detective story? Do you believe the answer lies in a vast, hidden population of ancient galaxies? Or does your mind lean towards something more fundamentally exotic, a new law of physics waiting to be written? The conversation does not end here. Share your own theories and ideas in the comments below. If unraveling the universe's grandest mysteries captivates you, subscribe for more journeys to the edge of our understanding. And always, always remember to look up at the stars, for they are full of whispers waiting to become a roar.